So we are the Thermal Imaging UAV Design Group. Our group members are Ty Craner, Jack Callis, Robin Migach, Michael Quigley, and myself, Austin Packard. Our advisor for this project is Professor Eric Pardiak, and he and the Environmental Fluid Dynamics Lab were looking to do research that required obtaining surface temperature data of large areas with high spatial and temporal resolution. The surface temperature data can be used to characterize the exchanges of momentum and energy for varying surfaces. So the way of collecting the surface temperature data is usually with various thermal camera systems, and all the existing solutions were inadequate for the lab's needs. So some current solutions that existed were to just use a ground-based thermal camera, but those were insufficient because they have a limited field of view and considerable image distortion. Satellites also provide this data, but at a very low spatial and temporal resolution. You can also use weather balloons outfitted with the proper equipment to receive this data, but they are extremely expensive to deploy. So we were looking to create a system that would be much more cheaper. So we ended up wanting to modify a drone, specifically a Lynx Motion H-Quad 500, to collect georeferenced thermal data. And the system consisted of a MLX 9640 thermal camera, a Raspberry Pi camera, a GPS receiver, various other sensors for determining metrics like heading and altitude, and a Raspberry Pi for logging all of the requested data. So some of our metrics for the design are that it had to collect spatial images with a spatial resolution less than 10 meters and with an ideal resolution of 2 meters, which we were able to achieve. It was desired to have to be able to cover an area of 1 square kilometer for the size of the image, which we were able to achieve. However, it's important to note that those two metrics are related. At a lower height, you can achieve a higher resolution, but at the cost of how far the drone is able to fly. It was desired to create a graphics user interface to easily create flight plans, flight paths, which we created. We also wanted to make it easy for the user to be able to retrieve the data stored on the drone, which was done by having the drone save the data directly to a USB via the onboard Raspberry Pi. It was also desired to have the drone weigh less than 1,500 grams. That is a number that we determined based on how long the drone can fly at a given weight. And we were able to achieve that by making several adjustments to our hardware to cut down on weight as much as possible. And we were able to get the weight down to 1,450 grams. And cost is a big part. We wanted it to be less than $500, which is significantly less than the other methods mentioned before. And we were able to, as currently outfitted, the cost is $350.
Excuse me, are you able to hear me now? Okay.
Oh, we can hear you now.
Sorry.
Yeah, here we go.
Okay. So, as I mentioned, one of our primary goals was making this as accessible to the researchers as possible. So that was our goal when designing the software as well. So first of all, we have a data collection system that prioritizes ease of access. So in some of our prior iterations of our design, we had the data saved to separate files. So the images, for example, would be saved to individual files that would then have to be associated with the other metrics via something like the timestamp or the GPS coordinates. And in place of that, we are now using a single file, a single comma-separated value file, essentially a spreadsheet that stores all of our data collected with a single update interval. So this way, all of the data have an associated GPS coordinate and time. And in addition to that, we designed a user interface to allow users to plan flights very easily. And this interface allows the user to specify parameters like the camera resolution and field of view and the desired resolution at the ground, and then select an area of interest and generate a flight plan. and then the user can export an XML file with the altitude and the GPS coordinates described inside of it and upload that to the drone. And we have a demonstration of that process as well. So here's the map view that the user would see. And on the right, have a bunch of controls. So here are the camera parameters. We have some settings for the map itself. So we use a street map like here, or we could use a satellite map. We have settings for the drone and the desired resolution at the ground. So we can go zoom in here. This is just an example map. We'll fly over President Circle, and this generates the actual flight plan, and it gives some hints to the user. It says this is above 400 feet, which we have to register with the FAA. So you might want to choose a lower resolution to fly at a lower height or lower number for this. And we can see that that changed the flight plan and increased the that we have to fly, but it also increased the resolution and dropped the height. So that's no longer above the 400 feet. And then when the user is satisfied with this, they can click submit and save. And this will save it as an XML file. So if we open this, we can see the different waypoints and the altitudes associated with this. And that can upload it to the drone to complete the flight.
Okay, for the hardware implementation, we just 3D printed all of our hardware. The landing gear is just one piece for each of the legs. There's no screws or anything like that, just attaches directly to the motor brackets. We have 2 separate camera housings for each of our thermal camera and optical camera pairs. You can either mount directly on the bars for the gimbal, or you can mount on the gimbal itself. And then we have a Raspberry Pi and sensor housing. So if you look, the top image right here, that holds the Raspberry Pi, that slides onto the bars, and then there's an optional press fit plate on each of those mounts where you can use a set screw and tighten it down further so it doesn't slide back and forth. On the bottom, that's like the sensor housing. So each of those rectangles is for the GPS, heading, altitude and pressure sensors. And then those just have screw bosses where you just tap directly into the 3D printed plastic to mount your sensors there. And then on the back end, there's actually a separate mounting spot for the temperature humidity sensor, because we didn't want any interference from the heat generated by the Raspberry Pi. And then I can just show a quick demo of our initial prototypes. So our first version of our landing gear, you can see right here, that was based off the OEM landing gear that came with the drone. It has this little foam wheel on the bottom, and basically all we did was just extend it down so we have enough clearance for all our hardware. And it had screw mounts here and a little press fit plate here. And the biggest issue with this landing gear was, 1, that it was too heavy, and 2, that it wasn't stable enough, and it could actually rotate this way if that press fit was loose enough. So for our second iteration, we wanted to make it more stable mounting, and we also wanted it to be lighter. It weighed over 200 grams. So we cut the weight quite a bit, and we came up with a different mounting system you can see right here. It's very similar to the final version. And that worked okay, but the problem that we had was when we did the FEA to design this landing gear, we only accounted for an axial load coming up from the bottom here. And after about 1 flight, it just sheared off for basically all of the landing gear that we had on there. So we went back to the drawing board for the FEA, and instead of an axial load, we put a transverse load coming here And so with that result, we came up with our third and final iteration of the landing gear. It's more of a combination of the first and second. We have a thicker cross section here. We added some material up here so this can't snap off. And I guess I'll show our sensor housing for the Raspberry Pi. And then you can see the temperature humidity sensor on the outside here. Kind of hard to see. And then here's our thermal camera package. And how that works is it's just two pieces and there's a hinge right here. So it swings open. You can mount one camera here, one camera here. Again, it just screws directly into the plastic. And then I guess I'll go to our original Raspberry Pi sensor housing. So we just started by making a Raspberry Pi case, just very simple, access to all the ports. And then we have this bigger box here. And the idea was that that could just slide into this box. You have space for an external battery up here and then all your sensors down here. And then the way that this was going to mount to the drone is from these arms right here. That would slide in this. And that worked well enough, except for when we were flying, it wasn't very stable and it was able to swing back and forth. So combination of it not being stable and too heavy, we went back to this design and then just built out from there. And so overall, all of our hardware only adds 250 grams to the mass of the drone, which is only 50 grams more than our original landing gear. So that's it for that. And I will start the screen share back up.
So I guess we'll get started here, but during the process of designing the drone, we performed tests to ensure that the drone was operating reasonably. The data that we received from the sensors were accurate as well. So the first test that we performed was a weight test to determine how much load the drone can withstand in the flight time that corresponds with that load. So we're going to show you two videos. Before we did the weight test, we were kind of ignoring that and we didn't realize how much of an issue it would actually be. So in the first video that we'll show you, it's going to be before we ended up finding out how much the maximum load of the drone is. And as you can see, it has a difficult time even trying to get off the ground. And when it does get off the ground, at most it goes about a foot. When we were performing or doing our first flight tests here, we were collecting data and everything as well from our sensors, but as you could tell, the drone just wasn't able to get off the ground. So we then performed the weight test to see how much weight we could actually add on to the drone to be able to have it fly for a significant amount of time and not be restricted to the height that it can reach. And this is where it's at now, after we did with the weight limitations that Mike was mentioning earlier. And with this, with the load that we have currently on our drone, it decreases the flight time by about approximately 20% compared to the drone with no load on it whatsoever. But it's still, even though that seems kind of significant, it's still within reasonable measurements. So the next test that we determined, or that we did, was for the thermal camera, which we directed towards a plate with a controlled temperature and a known emissivity. We measured the temperatures from the plate with the thermal camera, and then we also measured them with a thermocouple, and we compared the two results that we got from those measurements. And what we were able to find was that the thermal camera was able to have accurate temperature measurements compared to the results that we got from the thermocouple, and this was ideal for our project. And then the last test that we performed was for the GPS, and we performed this by locating recognizable landmarks, marking the coordinates to compare them to the data that we received from the GPS when standing at those landmarks. And from this, we were able to get the results that the GPS is accurate within 10 meters Unfortunately, this limits the spatial accuracy of the data that we collect, so it is a significant limitation to our design.
Like you mentioned, there's a few different limitations to our current prototype. For as far as for most of our prototype, we had the camera on a gimbal mount, which is ideal since we can take pictures with minimal distortion. But we found that with the gimbal mount attached, as you saw in that video, that it wasn't able to fly. We think that it's due to weight and also due to possibly where it was mounted. It was causing the front rotors to compensate, making flight almost impossible. Once we removed the gimbal, we were able to fly the drone again, like in the second video. So our final design was to eliminate the gimbal mount from the drone, which means that the images that we capture are no longer guaranteed to be pointed directly at the ground. So having a gimbal mount is ideal, so possible future improvements could focus on that. Our original camera that we planned on using was a FLIR Lepton 3.5. But we were unable to get it to interface with our current system. The Lepton 3.5 was ideal since the resolution was high enough that it could cover a large area with minimal flight time and few pictures while still meeting our design metrics. After significant effort with the FLIR Lepton, we decided to go with the MLX, which is an older model, but we knew we could get it working. We think that the problem was because the Lepton 3.5 was a brand new product and had limited support for the Raspberry Pi. Future work might focus on improving the camera to a higher resolution, since this will, like I mentioned, decrease flight time and the number of pictures needed to capture a target area. And with our GPS tests, it was shown to be accurate within 10 meters, which is larger than our spatial resolution goal, which is not ideal. Since this makes our GPS accuracy, because we want our GPS accuracy to be close to or less than our spatial resolution, just so we can make georeferencing accurate. With more accurate GPS technology, for example, like a differential GPS, we can increase our accuracy, which would also increase the usefulness of the gathered data. A differential GPS in this example would be prohibitively expensive in the context of our project and would complicate the data collection process because of its reliance on measurements from the ground. With our current hardware, we also installed a Raspberry Pi camera that could be used in the future to correct for emissivity. This process could be quite involved since it would require some sort of machine learning and known surface emissivity values, various things in the thermal data, but correcting for emissivity would increase our accuracy of the thermal camera data. We would also like to acknowledge our advisors in this project, Professor Pardiak and Travis Morrison of the Environmental Fluid Dynamics Lab. Their financial support and mentorship has been invaluable to the project. Thank you.